question today is this. How do you think this works? And camera people at home, it's like a sparkling, beautiful Christmas tree. So any guesses on how that Christmas tree works? What do you guys think? Maybe it's magic? It's kind of a magical time of year. Well, by the end of the class period, we're going to find out exactly how that sparkling Christmas tree gets its awesomeness. We're going to see exactly how that works. In order to get there, though, we got to do a little bit of physics. So I'm just going to kind of start by showing a little bit of what we did yesterday, and we are going to take that and we are going to try and add some numbers to it. We talked about how light travels when it goes from one substance to another and how it changes direction. I'm just going to go straight from there. We didn't have the fog machine out last time, so I'll show you that this time, and then we'll get rolling. What's that? Oh, I'll have to turn them on for me. Yeah, how about that? So there's the laser beam, much more easily visible. If there's actually, oh, for Pete's sake, it's doing one of its rest phases. Alright, well, it'll come back in a couple seconds. So the main thing to remember is that when you've got light coming in, it goes into the water at a certain angle, and it bounces out at the same angle, like the top is hitting the water. Some of it bounces right off the top of that water, but most of that light ray goes all the way through. And as it goes from air into water, it's changing directions, as you'll see right now, finally. So the beam goes in, and it goes in at one angle, but after it goes into the water, it changes direction, and it pops back out. Yesterday, when we were talking briefly about your rear view mirror, you can kind of see the two light rays right now. The one right here would represent the light ray that bounces off the actual glass of your rear view mirror in your car. This one right here. This one isn't nearly as bright. This one is the brightest because it hits all the way down at the reflective surface. And when you're in your car at nighttime and you flip your mirror so that you have the night setting, it's that dimmer light ray that you're seeing. So we want to figure out exactly what's going on with these light rays and their directions. Thank you for the offer, though. I'll make use of that. So we got to continue our notes from yesterday. So loosen up those hands and fingers, and if you have a calculator, you can get it out. If not, that's okay too. As you do that, I'm just going to go ahead and pass out a worksheet for this section. This is due Wednesday. So there's the quiz on Tuesday. This will be due on Wednesday. You're welcome. And again, when I say it's due, that means that I want it attempted as good as you can get it. Don't sweat it if you have trouble with some things. Just make sure that you do your best with them. This is a worksheet that we'll be spending a lot of class time on. I think I have a full class period dedicated after it's due to just kind of going through it and having you guys help each other out and having me come around to see what you need extra help with. So we talked about refraction yesterday. Refraction, again, is the way that light bends when it goes from one medium into another. like air into water or water into air. Doesn't matter how you really do it. Refraction is what's going on when light bends. So we got to figure out what's going on with light bending, and by the end of class we're going to see exactly what that has to do with that thing. So you can title your notes Refraction 2, or you can just keep going with what we did yesterday. Either way is just fine. So the main thing that we're going to be talking about is a mathematical relationship between the angle that light rays come in and go out and the type of substances that they move through. So the law that we're going to talk about today is called Snell's law. You don't have to write down what it's called, just write down the actual law here. Can you see through the Christmas tree, or should I move it down?
No, I can see past it. There's just a glare.
Oh, okay. So this is just a mathematical relationship. We talked about indexes of refraction yesterday, and these are numbers that represent how light travels in a certain substance. The higher the number, the more tough it is for light to go through it, and the slower it will be. This represents an angle. So 1 represents the first medium the light's moving through, the incident angle and the incident ray. 2 represents the second medium it's traveling through, and that's going to be the refracted angle, the refracted ray. So I'm going to go through 2 of these examples, 2 or 3, and then we'll see how you do with them, and we'll uncover some magic in the process by the end of it. Dotted line is the normal line, if you remember. And let's say we've got a light ray coming in at 60 degrees. So that's our incident angle. We'll say that this is air. We'll say that the bottom is water, just like the example we've been doing. The index of refraction of air, I'm just going to put a little a next to the n. If you want to leave it as the number 1 instead of putting a letter there, that's totally fine. I just put a so I remember that it's for the air. And that index of refraction is 1. The index of refraction of water is 1.33. Those will be the 2 numbers we use most often when we're doing problems like this. So of course the light ray goes from air into water. Is it going to bend down or across? It's going to bend down, just like you saw in the example. So that's what's happening. You can probably guess what we're going to try and figure out here. We're going to try and figure out what that angle is. In other words, angle number 2, I'm going to put a little W next to it so I remember that it's the angle that's being made inside the water. But however you want to label these is just fine, as long as you're being consistent. Your labels for this stuff down here should be the same, and the stuff for up top should be the same as well. So if I want to figure this out, I plug the numbers into Snell's law. So N1 is my first index of refraction. That's air. It's the first thing. So 1 times the sine of the angle, which is 60 degrees, is equal to the second index of refraction. That's water. So that's going to be 1.33. And I multiply that by the sine of this angle. And I don't know that one, so I'm just going to leave that as angle W.
Where did you get the 60 from?
This right here.
Yeah, but like, how did you get that?
It's like if you were given this problem, it would be given to you.
Okay.
It's just whatever angle that light ray makes with respect to the vertical.
And the same with those with the 33.
With this over here?
Yeah.
This is like, it's a known value. It's the known index of refraction of water. So We just kind of got to take those as givens. So from here, it's just a math problem. We got to divide both sides by 1.33. That's equal to the sine of our angle. And can anybody tell me where we go from here to actually figure this out? Anybody remember from math class? So once we get, what's that?
Is it sine then negative 1?
Yeah, exactly. Yeah, so when you get to this point, if you need to get this angle by itself, you need to take the inverse sine over on this side. Because, we can't divide both sides by sine. In order to get this sine over... Hello, God. In order to get this sine over here, what we have to do is we have to take the inverse sine of this side. And then our angle will be all by itself, and we can get that number. So if you were to go ahead and do that on your calculators, you would get 40.6 degrees. It's also important to note that if you're going to be using your calculators for this, especially your graphing calculators from math class, they have to be in degree mode, because we're getting a degree for this. Questions on how this works? Does this make sense? Okay, cool. I got another example I'll show you. So in this example, we were given everything except that angle. For the next example, we're going to be given everything except the index of refraction. And you can use the equation to solve for something like that just the same. So for this next example, we're going to say we don't know what this second medium is. We don't know what this substance is. But the top one remains air. And as long as that remains air, the index of refraction remains 1. Got a light ray coming in rather steep this time. The angle is going to be 20 degrees. And it's going to pop out at an angle of 15 degrees. So light ray coming in, 20-degree angle. We know that the index of refraction of air is 1, so we know everything about the stuff up here. Down here, though, all we have is the refracted angle. And using just that information, we're hoping to be able to figure out index of refraction 2, whatever the index of refraction of this material is. So that's our goal in this one, is to solve for that value. And in order to do that, we use the exact same process that we used for the last one. We start with Snell's law, and we see where that thing takes us. So in this case, index of refraction 1 is air, so that's 1, times the sine of the angle, sine of 20 degrees. That's going to be equal to index of refraction 2, which we don't know, multiplied by the sine of 15 degrees. If you're ever confused on which numbers go where here, just realize that this on the left is one material, this on the right is the other. So this is like everything that's going on your top material, or wherever your light ray is beginning. This is everything for where it's ending, wherever it's going to. So if we get to this point, we just have to get this index of refraction by itself. So we divide both sides by the sine of 15. And if you do the math, and you plug it into your calculator, which would be in degree mode, you would end up with 1.32.
How do you check to see if it's in degree mode?
I think there's a mode button. It might be something where you have to press second.
I don't know.
You know where it says second? I got it.
Now this index of refraction is unitless. It doesn't have any units like seconds or meters or anything. So it just kind of is what it is. Let's do another example here. Now we're going to have a light ray coming up from underneath.
So, for the last one.
Yeah.
Sine 15, and like you divide it. That's how do you get that?
You might have to make sure your parentheses are all in the right places. Because when you're dealing with a graphing calculator, you got a lot of times there's parentheses everywhere. Let me take a look real quick.
You just have to close the parentheses. Oh, okay.
Oh, there you go. Very good.
Thank you.
Yep. So here's our next example. We've got a 50-degree angle coming in, and we're going to go from air into water again. So now my index of refraction here is 1.33. That's what it always is for water. Air is still 1. And remind me, what happens when I shine a light ray from the bottom and it comes out the water, goes into air? Does it bend across or does it bend up? Bends across. Yeah, for sure. So like if I had the laser beam again, we'll just test this. And I have it coming up like this. You can kind of see the dot on the wall there. And so it's over there because it's bending across. So if I want to figure out the angle that it's making on the way out, I have to do Snell's law once again. All right, here we go. I'm going to use blue. It's a little bit, this marker has a little bit more life left in it. So even though in the past we've been using the top as index of refraction 1, that's only been because we started up here. For this example, we're starting down here in the water. So now the water becomes the first index of refraction, and this becomes the first angle. So index of refraction 1 is 1.33 times the sine of our angle. Now, the reason that I stopped right here is because this 50 degrees is not going to go right there. Did anybody pick up on why that might be? You got to be like super observant with the last two problems we did to see this. Yes?
Because you have 50 for like the second half of the problem, the water part, not the air part.
Good guess. Not quite, though. The 50 will be for the first part, because we are starting in the water here. Nope. That's okay. Good guess. So, in the other two problems, the angles that we've been using have been with respect to this dotted line, to the normal line. They've been this angle, and they've been this angle, not the horizontal one. These angles in blue are the ones that we always have to deal with for this law to be true. So because this is listed as a horizontal one, we have to instead figure out what this angle would be. And of course here it's going to be 40 degrees because it's got to be in total of 90. So just be aware, if you're given this angle with respect to the horizontal, you need to use that to find the angle with respect to the vertical. So this is going to be 1.33 times the sine of 40 equals the second index of refraction, which is air, times the sine of our angle, which we don't know. Say angle in the air. I better.
Very popular.
I guess so. I wonder how many emails I get on in general every day. My guess would be 60. It's a lot to wade through. So if this is what we have, and that's as a teacher, not just like personal emails. So in order to get this angle by itself, we have to divide both sides by 1, which is nice and easy. We don't really have to do anything with that, so we can just cross out the 1 if you want. In order to get the sine over here, though, and keep this angle by itself, as you guys mentioned before, we have to take the inverse sine of what's on the left. So the inverse sine of 1.33 times the sine of 40 degrees will be equal to the angle that this light ray makes when it comes into the air. And if you throw that in your calculators, I'll give you a second to do that. It's good to practice this. Good question. I would like you to round to 3 digits. So all that means is if you've got a number like this, if you want to leave it that way, that's fine. For me, when I'm rounding for the answer keys and everything, I round to the 3 digits. So for me, this would be 1, 2, 5, with all those zeros. And I do that for a lot of reasons. One reason is because you probably want to write this in scientific notation anyway. To be 1.25 times 10 to the whatever for scientific notation. This would also mean if you've got a very small number, that I would round this to 3 non-zero digits. 1, 4, 4 is what I would round it to. So as long as you got 3 digits that are not 0, that is how I personally round. But if you want to be more specific, I'm okay with that. Questions on how that works? Okay. So what did you get when you put that in the calculator? Anybody get a number they're confident in? No?
58.750.
That is totally worth being confident in. Yes. 58.7 degrees. If you're getting different numbers, be sure to see me at some point so we can iron that out. Now what I'd like you to do is I would like you to do this exact same problem, except I'd like you to change this angle from 40 degrees, and I'd like you to make it 60 degrees. See what pops out of your calculator for that answer. Yes. Yes.
I'll do this first.
Cool. On your way out, just fill this out as far as you can then. Make sure to put this in your calculator, see what pops out. I'll come around and just kind of see what you guys are doing. What'd you get on your calculator? You got an error.
Yeah.
Really? Is everybody getting an error? Well, this is absolutely fascinating. That's exactly what you should get. You should get an error on this. So the question is why? Why are we getting an error on our calculator for this angle? Because it only goes to 90, that's true. But like in terms of the real world, what's happening with this light ray that we're not getting some kind of exit angle? Yes! This light ray, if it is coming in at an angle at 60 degrees, it's not leaving. Let me show you. Alexa, can you turn the lights off on your way out? So we did this, where the light ray's exiting, and you can kind of see it there. But that's only if I have a very steep angle. If I make this angle shallow enough, look at what happens. This light ray is trapped inside this tank of water. It's not allowed to leave. It's just sticking in there. And that's what's happening when we have angles that are too shallow and they're going from an object that is slow for light to an object that is fast, like from water into air. We have a special name for it. It's called total internal reflection. And it occurs in all sorts of different things. I'm going to explain it real quick, and then I'll show you an example of this in the back of the room. You should indeed get an error on your calculator. If you did, you are not in error. You are 100% correct. Let's get rid of all the fluff here. So let's say we have an angle that's pretty shallow. And remember how we explained this yesterday? With, suppose I turn the light on for the people at home. So, we've got ecto 1, and it is in the slow medium, and it's traveling slowly, because this is the water, this is the slow medium, and eventually the front left tire gets into the fast medium, the air, and so this tire is moving faster than this one. That causes the car to turn this way. That's why light bends at that angle when it goes from something that's slow, like water, to something that's fast, like air. But what happens if we go at a shallow enough angle? If we go at a shallow angle, and this wheel is now going so much faster than this one, and the car begins to turn, just like the light ray, eventually this wheel might not even make it out of the slow medium. This wheel could go all the way back around. It's a ghost catcher. And then the car would just go back downwards, and that's exactly what's happening with the light ray. If you come in at a shallow enough angle, you're going slow, slow, slow. Now this wheel is moving faster, causing the car to turn down to the left. And if it's a shallow enough angle, the car's not even going to make it out. It continues that turn, and it goes right back where it came from. And that's what's happening with this. It's called total internal reflection. I'll just show you a quick example of this in the back of the classroom, and then we'll finish with a little bit of the math behind it. I'm going to go ahead and just kind of, if you can sort of just come back and like maybe start here and then just come back 6 feet between each other and then head back to your seats. So just spend like 1 or 2 seconds.
Come on, guys, let's go.
So I'm aiming this laser beam at the water as it comes out. And it's making the entire stream of water green, up to about halfway down the sink. And so what's happening is this laser beam is remaining inside that stream of water because it's coming in at a very shallow angle. It can't leave the water, it's stuck inside. And that's an example of total internal reflection. You just fill up the pass on the front. And I'll sign it for you. So that's what total internal reflection is about. And folks, that's exactly how the Christmas tree works. And we'll kind of close with that at the very end. Right now, though, I just want to show you the science behind the math of this. So total internal reflection occurs when you have an angle that's big enough. And you're moving from a medium that is thick like water to a medium that is thin or easy to move through like air. This does not work if you go from air into water. You always have to be going from something that has a high index of refraction to something that has a low one. So there is that one particular angle at which that light ray is not going to leave. And that's called the critical angle. So you can put this in your notes. And the math equation for the critical angle is simply this. It's the inverse sine of index of refraction 2 divided by index of refraction 1. And that tells you the angle at which light will no longer be able to leave that medium. So if I would do this using my calculator, that's as fancy as I get. Good old TI-30 from 5th grade. So we did water, right? In the last example. Our angle of 40 degrees in the second to last example, that one made it out. But when we changed it to 60 degrees, it did not. We got an error. So our critical angle is probably between 40 and 60 degrees. Well, let's see. If we're going from water to air, then water would be down here, air would be up here. So 1 divided by 1.33 is equal to big decimal there. And I just take the inverse sine of that, and I get 48.8 degrees. So 48.8 is the angle at which light will no longer leave that water. And that's exactly what we would expect, somewhere between 40 and 60 degrees. Questions on the math? Okay. So where this comes in handy for the Christmas tree is all that Christmas tree is a bunch of little strings there, right? You ever heard of the terms fiber optics? That's exactly what fiber optics is. You've got light coming in to these little strings from one location, and the light bounces around until it finally can exit at a large angle. So, and I'll show you this. I'll come around with it in just a second. But what's going on, I'll come around with it now. What's going on is if you look real close, you can see tiny little circles on the bottom of this. And each of those circles is one of the little fiber optic strands. And the light goes into each of those strands, and it comes out at the end of the strand. In between, the light's bouncing around inside until it finally reaches the edge. So there's nothing magical going on in the little base of this Christmas tree. It's just light that's being cycled through on a little color wheel. Try not to get this so that it blinds you, but it's just a color wheel that's going back and forth and around and around. So we don't even need this color wheel. We could unplug this. And maybe you want to have a Christmas tree that does something else. I love teaching this class. Let's see. I'm going to try and make it so the camera can actually see this. Let's say you just want to have a Christmas tree. And maybe you buy this for $1 at Goodwill or something because there's no workable base. All you got to do, take the flashlight on your phone, stick it on the bottom, and you can make your own little light show. Light rays are bouncing around through those strands, and they finally leave at the end when the angle is big enough. Maybe you want to add a little color to this. Maybe you're feeling a little romantic, so you take a little red laser or a red light and you move it around. You can do it slowly, or you could have it like a rave or something. And of course, they got to use the green laser, wherever it is. Alexa, you want to hit the light for me? Thanks. Okay, turn it off. So fast, or you go slow, whatever your heart desires. Because that's what's going on with fiber optics. Yeah, and again, thank you. Okay, you can go ahead and remember, worksheet 5 is not due when you get back. It's due on Wednesday. Quiz when you come back on Tuesday.
Mr. Kutcher's classes for the rest of the day. Mr. Kutcher classes, please, when you go to those classes, those will all be work days. Please bring stuff on which to work. Mr. Kutcher students are work days the rest of the day. Thank you.
I'm gonna drop it.
Light bounces around and exits at the end of the strand. The end.